Hey everyone, welcome to the review for the final exam. This is going to be pretty much your last presentation that you'll have to watch this semester. I am going to do it a little bit differently though, so instead of watching this one video that is going to encompass the entire semester, it's going to be split into two different videos. You'll still watch the same video from before that covered the midterm, and in this video is basically going to cover the second half of the semester. So let's get right into it. Things we're going to be talking about: flux core arc welding, testing of welds, gas tungsten arc welding, and we're going to talk a little bit about the various cutting processes. So as we move into flux core, we're going to break this down even further. We're going to talk a little bit about the equipment that is used for flux core. We're going to talk about the electrodes, shielding gas, and then also modes of transfer. Some of this should sound a little familiar to you. We talk about a lot of the same information when we start moving from one welding process to the other. So as far as flux core arc welding is concerned, there are a lot of different applications that you can use flux core with. Honestly, it just depends really on what you're trying to do. You can weld thin material with it. You can weld thick material with it. The only thing that kind of gets decided at that point is what electrode you're going to use, and we'll talk about that later on. Just know that it's very widely used out in industry, especially in structural work. So anything like bridge work, building erection, that sort of thing, like you'll find flux core being used. If you've heard the term iron worker, I want to say, like, back in the day, iron workers were mainly like stick welders, but now the term iron worker is more related to welders that use specifically flux core. Some of them still use stick welding. I guess it depends on what union you're in, but for the most part, a lot of iron worker unions use flux core. It's, again, the combination of like the best parts of gas metal arc welding and shielded metal arc welding. So you have the ability to make continuous long length welds, like with GMAW. However, you have the penetrating capabilities of shielded metal arc welding. And where shielded metal arc welding had a bunch of good things about it, one backside to shielded metal arc welding was, you can lay down anywhere from 5 to like 8 inches of weld, and then you have to replace a welding electrode. And so the efficiency or the productivity rate of shielded metal arc welding is lower than that of gas metal arc welding. And so with this, you can almost think of it as like MIG welding, but with all the good stuff about stick. All right. So it is a constant voltage welding process. So you can think of anything that has a spooled up wire being fed through a welding gun is going to require constant voltage. And constant voltage allows for constant stabilization of the welding arc. You can almost think of it as also saying maintaining a consistent arc length. So as the wire touches down to the base material, heats up, and then melts off, depending on what mode of transfer you're in, voltage really plays a key role here in stabilizing the arc every single time that wire touches down, in cases like short circuit, or just in the event of, say, you're using something like spray where you have that constant voltage just maintaining the arc length and those times where you might be getting a little too close or a little too far away. With that being said, all flux core welding operations are done on direct current. So you'll either be using direct current electrode positive or direct current electrode negative. And so the reason why we don't use alternating current with flux core is because of that inner flux core. So as we're welding, that flux that's on the inside of this wire has to get heated up. And so we need that constant heat to heat up the flux on the inside. That way, once it enters the arc, sprays across that arc, and it becomes part of the weld, that flux doesn't get trapped under the weld or, cause all kinds of problems. And the thing about alternating current that makes it so hard to weld with flux core is, hundreds of times a second, your polarity is changing from electrode negative to electrode positive. So that means like over 100 times a second, you're actually reaching 0 amps in order for that polarity to change over to the other side. So there's a lot of sloping up and a lot of sloping down. So that makes it really inefficient to use a flux core on alternating current. So it's going to be direct current, and from there it's either electrode positive or electrode negative. That's all going to depend on what type of electrode we're using. And again, more on electrodes later. And so like I said before, this is a wire-fed process. So everything that we were using with gas metal arc welding, more commonly known as MIG, we're going to be using the same stuff, or it's going to appear the same with flux core. We're still using a wire feeder. So if we take this being the power source down here, we have our wire feeder, we have our spool of wire. And so remember, some machines have the wire feeder built into it. So some of them do have it on the outside. Some flux core electrodes do require shielding gas. The one that we were using in class did not. You'll get to use a flux core electrode that does require shielding gas in the more advanced course. So more to follow later if you end up enrolling in that course. We still have a MIG gun, or you can think of it as like a flux core gun, and there are different variations of that as well. And we still have a ground clamp, okay? So a little bit more about the electrodes. So when we start comparing the electrodes from gas metal arc welding to flux core arc welding, there's a big difference. When we're MIG welding, we're using only solid wire. So if you were to take some wire cutters and snip a piece off, it would be solid from one end to the other, or basically one side of the wire to the other. With flux core, however, if we were to cut a little section off, we would be able to see that it's hollow or tubular, and there's some stuff on the inside. That stuff on the inside is the flux. So if we think back to stick welding, or more we should be calling it shielded metal arc welding, the flux on the electrode burns off and then pulls impurities from the surface of the base plate and rises to the top and then forms that slag layer. So that's exactly what the flux in flux core arc welding does. It acts the same way as the flux from stick welding. And here's a really basic view, or a basic way to look at the classification. So every welding process that we're using, the electrodes are going to have an identifying name. It's going to have a classification, which is just a series of letters and numbers that tell you a little bit more information about the electrode. So the electrode that we were using in class was E71T-8. So if we take a look at this basic breakdown of the classification, if we take the first letter E, that stands for electrode. And almost all the time, the E is going to stand for electrode. Now there is no R, and that's because you cannot find flux core electrodes in the form of a filler rod. So it's just E, and then numbers, and then so on. So the next thing, X, this first X, or this first placeholder, that tells us the minimum tensile strength. So another difference from flux core from MIG welding. So in MIG welding, the first two numbers told us the tensile strength. In this case, with flux core, the first number tells us the tensile strength. So in the event of using the same electrode from class, E71T-8, that 7 tells us that the minimum tensile strength that this electrode will give us when properly used is going to give us 70,000 pounds per square inch, Or if we thought of it in terms of KSI, it would be 7 KSI. Now the next digit is going to tell us what positions this electrode can be used in. So back to E71T-8, we would take the 1, and that is going to translate to we can use this electrode in all positions. So you're either going to see a 0 or a 1. If it's a 0, then it can only be used in the flat and horizontal position. These electrodes are typically higher, they have higher deposition rates, so they're a lot more difficult to use in the vertical and overhead positions. So that's why there's these two groups. One of them is flat and horizontal only, the other you can weld in any position. Now the letter T. So if you were to see something else here, say like the letter S, you would automatically know that this is not a flux cord electrode, because S would stand for solid, but in this case T, this stands for a tubular electrode or flux cord. Okay, so E71T-8. And now the last digit that we're going to be focusing on in this course is the number 8, or signified by this placeholder here, and that's going to tell us the usability, performance, and impacts. Basically, it's letting us know the chemical composition of the electrode, what polarity it can be used, and some other little tidbits. And so we can look at all of that on this chart right here. This is just a more in-depth look at the various electrodes that are available for flux cord arc welding. So we can work all the way down and we'll find this one right here, EXXT-8. Or if you were just to plug in the electrode that we've been using, E71T-8. So if we just go directly to the right, you'll see all the information that pertains to that electrode. So if we look as far as recommended weld passes, E71T-8 can be used to make multiple weld passes. Now, this doesn't necessarily mean that, oh yeah, I can do more than one weld on this entire project. I can weld over here, I can weld over there, I can weld on the bottom side, the top side. No, it's not really talking about that. What it means by multiple weld passes is if you were doing, say, like a T-joint, and instead of welding it with one single weld, you can stack welds on top of each other to make that fillet weld even bigger. So there are some electrodes that you're technically not supposed to use for multi-pass welds. It's you put down one weld and that's it, you're done. So this electrode, you are able to do multi-pass welds, which is just another reason why it's so widely used down in industry. And we can also see if this particular electrode requires shielding gas. So E71T-8 does not require shielding gas. And then if we look over here, this chart also tells us what current and polarity we're supposed to use with this particular electrode. And so you can just start from the top of the chart and go all the way down, and you'll see that it basically everything here is direct current. So the only thing you have to worry about is whether or not it's direct current electrode negative or direct current electrode positive. So E71T-8, we use it on electrode negative. And this, remember, think back to polarities. So when we're using direct current electrode negative, that places roughly 70% of the heat created by the electric arc, it focuses that onto the base plate. And then the other third is going to be projected onto the electrode. So typically, direct current electrode negative gives us better penetration. And just quite the opposite, if we were to be using direct current electrode positive, 2/3 of the heat would be focused onto the electrode, and then the other third would be projected onto the base metal. And so I'll go ahead and I'll leave it here, give you some more time to look at this chart if you need to, or you can always pause. We'll keep it moving. So let's talk about the modes of transfer. So if we think back to gas metal arc welding, when we're using wire-fed processes, there are three types or three different modes of transfer. There's short circuit, there's globular, and there's spray. So short circuit is probably one of the most commonly known modes of transfer. Maybe not the most commonly used, but it's the most commonly known. It's the easiest mode of transfer to weld with if you're learning how to use this process. Now, short circuit is also used with the lower range of voltage and wire feed speeds. And then there's spray at the opposite end of that spectrum that's used with higher wire feed speeds and higher voltages. So spray mode is what the industry requires in many different instances, and that's because it gives you just an all-around higher quality weld. Now there's a problem here. We cannot use short circuit with flux core. And if we think back to what I was saying earlier, the flux needs to be preheated before it actually melts off. And so if we're using short circuit transfer, that flux cannot be properly heated in time so that by the time it reaches the arc, burns off, and then mixes with the weld puddle, all kinds of bad stuff is going to happen if it's not preheated correctly. So we cannot use short circuit transfer. That leaves us with globular and spray mode. Now we can take a look at these two images here. So one image here displays self-shielded flux core to arc welding, which is just another fancy way of saying flux core to arc welding without shielding gas. And then there's dual shielded flux core to arc welding, or basically flux core with shielding gas. So in either depiction, you can see more or less the same elements. You see the different parts of the welding gun, you see the electrode, you see the different parts of the weld puddle, the weld itself. The only difference is that one, the shielding gas is basically provided by the flux as it burns off. And the other one has two types of shielding gases, one that comes from an external source and one that's created by the flux as it burns off. So what I want you to look at here is right in here, right at the tip of the welding electrode. This is where your electrode becomes the weld metal droplets that spray across the arc and enter the weld puddle. Now, if we remember from gas metal arc welding, we want to be in spray to be the most effective, to have the most, the best quality welds. And globular, while sometimes some people use it like in the flat and horizontal positions, it actually gives you a lot of spatter. It's not a very clean arc. It's not a very stable welding arc. So where globular used to be used more in the past, now you can think of globular as just kind of like a stepping stone from short circuit to spray mode. So in a lot of cases, the machines that we'll be using, any of their recommended variables like wire feed speed and voltage is already going to place us in spray mode. So as we're welding with flux core arc welding, you'll probably never see globular unless you really turn down your settings. But otherwise, if you use recommended settings, you should always be in spray mode because that's what's most effective for flux core. And here's just a comparison of globular versus spray transfer. So globular, basically what it sounds, the electrode just literally becomes globs of metal. Versus spray transfer, there's a little bit more control in how the metal becomes part of the weld puddle. Okay, let's start talking about testing of welds. So for the final, I'm just going to be focusing on quality of the weld and how the weld can be tested versus how welders are tested. So there's a lot of information that there was to soak in just among these two sections of the course. So I'm only going to focus on one. because your other following courses will pick up on how welders can get certified a lot more in depth. Again, this is just the intro course, so I was just giving you just the basics, so that way you're aware of what else is out there in the realm of welding. So we're going to briefly talk about codes, discontinuities, non-destructive testing, and destructive testing. So in terms of welding codes, you think of welding codes as like the rule book. So the welding codes are going to tell you everything you need to know about the work you're going to do. These like quote unquote rule books are out there to establish quality standards. That way, just not anyone who claims they know how to weld can go out and actually work on, very crucial high tolerance projects, and there'd be a risk that their welds fail and it becomes like a catastrophic issue. People get hurt, stuff gets damaged. Every code is in place to basically prevent that from happening. So depending on what you're doing, actually, let me start over. Depending on what you're doing, there might be a code that tells you basically how to do that work. If you're doing stuff like, just welding your neighbor's fence, like a simple repair, chances are there isn't really going to be a code for that, because that's not really, a situation where a failed weld is going to be catastrophic. I mean, for some people it may be catastrophic because that means more money they have to pay to get it fixed, but it's not like, someone's life is going to be in danger if it fails. However, welding on auto bodies or welding on a building, welding on a bridge, doing like stud welds for like rebar or anything like that, and, pipelines, all that is going to have a code that tells you basically how to do that work, and then also how to inspect it. So, depending on what you're doing, there could be a different code that you need to follow. There is no one universal code book. There are a lot of different code books out there, and later on you'll find that just the same goes for welding certifications. There is no universal welding certification. It just depends on what type of work you intend on doing. Now, there are a few different organizations that establish these codes or these rule books. The main three that we'll be talking about, and pretty much the main three that we deal with here in the United States, are the AWS, or the American Welding Society, ASME, which is the American Society of Mechanical Engineers, and then there's API, or the American Petroleum Institute. So these three organizations, depending on the work you're doing, they will more than likely have a code book that describes the work you're doing and how to do it. So the most common one that you'll hear in the program, or hear about in the program, is AWS D1.1, otherwise known as Structural Welding Code for Steel. Now, this book talks a lot about just buildings, so structural work when it comes to buildings. And this isn't like your, single family home or anything like that. This is like a corporate building, or like a manufacturing building, where they're actually using like large beams to set up the frame of the building itself. So every single weld is going to have a process or a procedure that it needs to be done according to. Now, if you're thinking to yourself, well, as a welder, this is a lot of information I need to take in. How do I know all the ins and outs of these different code books if I'm trying to just get a basic welding job and just make money to survive? Well, this is where code books kind of have this little, it's like who really deals with the code books? So welders, we do deal with the code books to a certain extent. We just need to be aware of what the code talks about. And if we need to know where in the code book to find it. But basically what it comes down to is we just need to know enough about the code so that way we know how to get certified. For the most part, everything else, the code books are going to be for engineers and inspectors, because a lot of the code book is basically telling you how to measure the quality of the welds that are going to be put down for whatever work you're doing. So engineers use that in order to design welds that the welders are going to be doing. And then the inspectors use these codes in order to inspect the quality. So really, we as welders, we only need to just be aware of the various codes that are out there and just know if the work we're doing is covered by either one or more of these codes. And so when we start talking about quality of welds, we start thinking of discontinuities. So if you think back to the module in the course, there are a couple terms we need to know: discontinuities and defects. So a discontinuity is basically anything that can occur within the weld that breaks up uniformity. So if you have a weld from start to finish and you see something in the middle or at the end or at the beginning of the weld that isn't supposed to be there and only occurs in this one spot or in a couple other spots, this is called discontinuity. Now it becomes a defect when this discontinuity occurs a certain amount of times, or it has a big enough presence to where it can cause the weld to fail. So welds can have discontinuities and still pass an inspection. It's when those discontinuities have too big of a presence that will affect the structural integrity of that weld, then it becomes a defect. And so some of these things will equate to an automatic defect. Some of these will just, kind of teeter that line of being a discontinuity or a defect. So real quick, the things that are, or that can be automatic causes for a failure, cracks. So any kind of crack is a no-go. Even if it starts out as a small crack, this crack can grow in size and that can lead to a catastrophic failure. So if there's a crack of any kind or any size in your weld, more than likely it's an automatic no-go. Incomplete fusion and incomplete penetration. So these two right here are going to be another couple causes for automatic fail. So just these three in themselves are going to be defects right away. Now, if we start looking at porosity, you can have a little bit of porosity depending on what code you're working to. Now, because there are so many codes out there, I won't throw too much information at you and say, well, in this code book, it's okay. In this code book, you can have this much. And in this code book, you can have that much. I'm just going to keep it real simple and say that some codes will say some porosity, it's all right. But if individual parts of that porosity are very large, or if they happen, so many times in a certain amount of inches, then it will become a defect. Undercut. Some codes will say that, a certain amount of undercut is okay. Some codes will say, nope, it is unacceptable. And then the codes that say that a little bit is okay, they'll tell you how much is okay. Slag inclusions. About 99% of the time, slag inclusions are automatic fail. And this is because this is something that has been trapped somewhere in the weld that can lead to cracks, and it can lead to other things going on that essentially mean a failure of the weld. And then the same thing for tungsten inclusion. So this is more for gas tungsten arc welding, where some people, maybe they were a little unshaky in the moment and they accidentally dipped their tungsten electrode into the weld, and then they broke their tungsten off, but instead of grinding out the tungsten, they were just like, it's whatever. If I heat it up high enough, it'll just melt and become part of the weld. Yeah, that's a no-go. So same thing, slag inclusions, tungsten inclusions, they can lead to failure of a weld. Now, arc strikes. Arc strikes, depending on what you're doing, again, some code books are very strict and they say, nope, any arc strikes, automatic fail. And if you're wondering what that is, think back to shielded metal arc welding and trying to start the arc. You remember when you were trying to learn how to just strike an arc, and you can tap the electrode to the metal like 100 times and you'd get stuck, and sometimes you'd pull the electrode off, and as you were doing so, you were kind of arcing across the plate. So arc strikes is just that. It's when you're striking the arc anywhere that is not part of the welded area, or the area that's going to be welded. And so why this becomes a defect is when we start looking back at metallurgy and the heat treatments of steel and what happens to steel as it heats up and cools down. Even though we could have just arced against one area of the plate for like not even half a second, still, for that half a second, we have changed the metallurgical composition of that area enough to where it could compromise the structural integrity of that weld. And of course, there's a lot more types of discontinuities out there, but just for the sake of time, let's just keep it moving. So here are just a few examples of a few of these discontinuities. So we have this one, porosity, where it's basically pinholes in the weld. And so you can see that there are various sizes of porosity, and then you have this big old huge porosity bubble towards the end of the weld. Okay, so something this big, I don't know what every code book says, but I'm fairly certain that if you have something this big, it's going to be an automatic fail. Versus something that's a little itty-bitty pinhole, depending on what you're doing, the code book might say it's okay. Some will say, no, you have to grind it out and completely redo it. This next image over here is of a crack. So you can see this is a pretty sizable crack. I can't see the end of the weld, but you can see here's the start, and it travels in this direction, and this crack pretty much begins at the start. And I think it'd be safe to assume that it continues all the way to the end of the weld. So obviously this is a good example of why cracks are defects and would cause a fail to be rejected. And then right here we have lack of fusion. This can also be called overlap or cold lap. This happens in a lot of situations where travel speeds are too fast, amperage settings are too low, or in say like times of gas tungsten arc welding, you're adding filler material before you've even established a weld puddle. So all you're doing is just dumping metal on the surface of your project, and you're not really fusing in. And then over here, this last image, we've got a groove weld where you're basically welding from one side to the other, and this is the back side of the weld. And you can see that on the first half of this weld, the weld fuses with the top plate, but you can see a clear separation between the weld and this bottom plate. So that's a lack of fusion. And then over here where we start looking at lack of penetration, you can see areas where the weld has come through all the way to the backside, and you've got some melt through. And then you've got areas where the weld did not make it all the way through to the backside of the plate. So this is lack of root penetration. And the same can be said for fillet welds. Sometimes you're just not welding hot enough and you don't really weld down right to where these two plates meet. Okay, so let's start moving on and talking about testing of welds. So very first series of weld testing methods is called non-destructive testing, or non-destructive examination. You'll hear these two terms a lot as you progress in this program. Just know that they pretty much mean the same thing. NDT, NDE, same thing. It's non-destructive inspection, okay? So they include visual inspection, which is the inspector, just looking at the weld with the naked eye and using some tools to measure discontinuities to determine whether or not they become defects. Then there's penetrant testing, which sees a type of liquid used on welds to identify, again, discontinuities. There's magnetic particle, which acts almost similar to penetrant testing. Think of it like you're using a super magnet to pull powdered steel to where the discontinuities are. There's ultrasonic testing, and then there's X-ray testing. So if we take a look at the first one, visual inspection. So over here, these are just a few of the tools that an inspector can use to visually inspect the welds. And so these are my personal tools. Even I don't have all of them. I just have enough to get me by. And so these tools right here are fillet weld gauges, and they can be seen in use over here, where the fillet weld gauges can be used to determine the actual size of your fillet welds. So when we start thinking back to weld symbols and how sometimes the size of the fillet weld is being given to us on the reference line, this is how the inspector can actually check to make sure that we've made the correct sized weld. Now this gauge right here is to determine reinforcement. So if we're doing a groove weld and an inspector thinks maybe we've put down a little bit too much weld, we can use this gauge to determine how high that weld is. And if it's over a certain amount, according to whatever code we might be welding to, it could pass, it could fail. Now this gauge right here is used to measure undercut. So this end of the gauge is inserted into the area where there's undercut, and then we can see how deep the undercut goes on this side over here. Now again, there's a lot more gauges out there that can be used. These are just a few, and just to kind of give you a working idea. Now we have penetrant testing. So this is using a series of liquids to test the weld. So there's three that we're using: a cleaner, a penetrant dye, and a developer. So it's as easy as just step 1, clean the metal. Step 2, spray some of that penetrant on the metal. Now you've probably seen this in pictures and probably didn't even know it's penetrant testing, but the penetrant dye is red and it gets messy. So if you ever find yourself, attempting to work as an inspector, just plan on not coming home with clean clothes, okay? Because this stuff gets everywhere. And then once you spray that on, depending on the dye you're using, you might have to let it sit for a few moments. Then you clean it off again. And now you're going to spray the developer on there, which it's basically all three of these come in a spray can. And the developer looks almost like you're spraying a film of chalk on top. And so once that happens, once the developer is sprayed on, if the dye penetrant has soaked into any discontinuities, say like cracks that you can't see, undercut that you can't see, lack of fusion that you can't see, it's going to come through and essentially bleed through the developer. So when you got this layer of what looks like white chalk on your metal, you can see all these little red spots come up of areas of the weld that, have discontinuities. So then after that, you clean your surface again, and you just fix the weld. Now here's ultrasonic testing. And I'm skipping past a few of the processes because I feel like they don't need any explanation. Like X-ray testing, I'm pretty sure most of us have had an X-ray or know what an X-ray is. And it's the same concept. You take an X-ray image of a weld, and boom, you can see any discontinuities there. So ultrasonic testing. If you think about like pregnancy appointments, where the medical professional uses a machine to, give you an image of what the child looks like in the womb. We use the same technology for inspection. However, the images come up in a different way. So the same technology is being used, but instead of being able to see a descriptive image of the defect or the discontinuity, it kind of comes up as a line graph. So we use the graph and we use, all these different rises and drops to identify locations where there is a discontinuity. And then depending on the material that you're testing, the position that you're testing in, all these different rises and dips are going to tell you different pieces of information. Now, I know it might not be an easy concept to understand, so I'm just giving you the basics now, and if you decide to take that class later on, it's all going to click. That light bulb is eventually going to come on. Alright, so let's talk about gas tungsten arc welding. So this was the last welding process that we got into. So we'll talk about some of the equipment, some of the auxiliary equipment that we may have accidentally used, but we weren't supposed to use a lot of the auxiliary equipment. So this is just to let you know that it's there. We're kind of going to go over the various electrodes and then the shielding gases. So for the most part, a lot of the equipment from gas tungsten arc welding and shielded metal arc welding are the same. They use the same power source, constant current. They will use the same welding machines. The only real difference is in the torch. So where shielded metal arc welding saw the use of an electrode holder, with gas tungsten arc welding, we're going to be using a torch. Now there are a lot of different parts of a torch. And so before I get to that, I just need to tell you that there are two types of torches. There are air-cooled and there are liquid-cooled. Now this has nothing to do with duty cycle. So if you think back to the duty cycle of power sources and how some have a cooling system, some don't, when it comes to air-cooled and liquid-cooled torches and gas tungsten arc welding, the only thing that has an effect on is whether or not your torch gets hot over prolonged periods of use. So out in industry, depending on what you're doing, you might have to be using a water-cooled torch because you're welding for long periods of time and you're welding at high amperages. So, again, this is one of those things where it depends on what you're doing. It's going to dictate what you find. And so with all of the different components of a torch, they're all more or less the same. Obviously, you'll come into sorry, brain farting. You'll come across various sizes and designs, but they all serve the same purpose. So you have your main torch body, and these little white sleeves here that don't really have an arrow pointing to them, those are your insulator cups. So those act as kind of like a secondary measure to prevent your torch from overheating. So you have your collet body, which screws into the torch, and this is what allows or basically focuses the stream of shielding gas through the ceramic cup and then out towards the weld. So once the collet body has been screwed into the torch, you'll screw the ceramic cup over that. Then you have your collet, which the collet is there to basically energize the tungsten electrode. So this electrode has to pull current somehow, and when it makes contact with the collet, the electrical current passes through the torch basically into the collet, and as the collet makes contact with the electrode, the current flows into the electrode, and that's what gives us the electric arc. Now, tungsten electrodes come in all different sizes and lengths. So, a brand new tungsten electrode is going to be fairly long, so you'll have a longer back cap. This one's a little short, And the purpose of the back cap is just to seal it all up, just to make sure that shielding gas isn't escaping through the rear of the torch. That's basically why it's there. So as you start coming across different lengths of tungsten electrodes, you also come into contact with different sized back caps. But they all serve the same purpose. Oh, and before I forget, so GTAW can be used with direct current or alternating current. So more specifically, when we're using direct current, you'll almost always be using direct current electrode negative. I don't think I heard anyone in the shop attempting to use direct current electrode positive, but if any of you maybe made that mistake and I just didn't find out about it, if you want to, feel free to share your experience with the class and with others. But yeah, so bad things happen when you try welding on direct current electrode positive with gas tungsten arc welding. So it's always going to be DCEN or AC. Now AC is going to be more for non-ferrous metals, so like aluminum, magnesium, that sort of thing. Direct current is going to be for like steel, stainless steel, pretty much anything else under the sun. And then one other bit of equipment that we came across gas tungsten arc welding was the remote. So this can come in a few different forms. This can come in the form of a foot pedal. And if some of you were lucky enough to use the Fronius machines that we had in the shop, the remote switch was actually built into the torch. So you would basically push a button when you were ready to weld, and by pushing that button, you'd more or less activate the welding arc. Okay, so one bit about the ceramic cups. I'm pretty sure many, if not most, many, if not all of you have noticed that there's a number that is stamped onto the cup. So the number on the cup tells us the size. So it's the opening. So the inner diameter of the ceramic cup corresponds to the number that's stamped on the cup. Everything is in increments of 1/16 of an inch, which can be seen in this chart here. So just about every single cup that we have in our shop is a number 7, which means that this inner diameter is 7/16 of an inch. Now, if you were to come across, say, like a size 10, all that would mean is your inner diameter is 10/16 of an inch. Now, this is an improper fraction, so you can break this down. So this would be 5/8. And so, like I said, it's all in increments of 1/16 in an inch. So whatever number you see on your cup, just kind of turn it into a division problem and throw 16 under it. So a number 5 would be 5/16. A number 11 would be 11/16, so on and so forth. All right, now as we start talking about auxiliary equipment, the very first thing that you've all been using, despite knowing it or not, is high frequency. So high frequency is what we use in order to start the arc. And I think there were a couple of you who may have approached me this semester and asked the key question of, I'm pushing down on my pedal, but no matter what I do, the arc cannot melt my metal. And when I go over there and I find that your ground clamp isn't hooked up, but that stream of electrical current that you're seeing is the high frequency. So high frequency can be thought of as just a very high or a very large amount of voltage that is trying to push that electrical current through the electrode and onto the weld piece. It's trying to start that welding arc. And if that circuit isn't closed, if you don't have the ground clamp hooked up, then that is all the arc ever is. It's just going to be that little bit of juice coming out the electrode or that high frequency, and it's never going to truly establish a welding arc. Now, this isn't dangerous. You can, you can shock yourself with it, but it's not going to hurt you. If anything, it's going to scare you. So if you've ever heard of people shocking themselves whenever they're TIG welding, more than likely it's because of high frequency, and it's either because their projects weren't grounded properly or they didn't tighten down all the components of their torch, and so a little bit of that current kind of jumps through. And there is also, well, actually, before I get to pulsar, let's talk about slope. So slope, we don't really use slope when we're using a pedal. We use slope more when we're using lift arc. And so lift arc is a method of welding with TIG that does not use the foot pedal. So this is where we make contact between the electrode and the base metal, and as soon as we break contact, an electric arc is established. So slope refers to upslope and downslope. So more specifically, upslope, whatever amperage you set your machine to, let's say 180 amps, just off the top of my head, instead of starting the arc immediately at 180 amps and potentially melting right through your metal from the get-go, slope actually starts your arc at a very low amperage and then over time increases up to whatever amperage you've set on your machine. So a lot of people will set a very low amperage so that way right off the bat they're not just superheating the very start of their weld. Depending on the metal that you're welding, you actually want a very low amperage to start with and then work up to that high current. Same thing with downslope. Instead of just cutting the arc right away, downslope kind of turns the volume down or turns your current down little by little, so that way it doesn't just shock the end of your weld, for lack of better terms. And then the pulsar is not something that we've used this semester. This is something that you'll get into when welding stainless steel. And so pulsar, what it does is it flips your welding arc back and forth. So you'll have two different amperages. You'll have what's called a peak pulse and a background amperage. So your peak pulse is what you actually set your machine to. Let's say 140 amps is what you want your peak power to be, but you want your back amperage to be considerably less. And this is to control heat input into your base metal. So if you're doing some kind of welding work where you want to, say, avoid distortion, you want to avoid burning through, or whatever it may be, if you want to just control heat input, then using the pulsar is going to be a good idea. So on the pulse time, so you can kind of use this image here, how it peaks up in current, stays there for a little bit, and then drops down to the background amperage, stays there for a little bit, and then goes back up to peak, and then after a while it drops back down. So the peak time is typically where you'll get your penetration and your fusion, and then your background time is when you would want to scooch forward in your weld. So think of it as peak time, you're melting metal, you're adding filler rod, and then on the background amperage, you're kind of scooting forward a little bit. That way you can just keep moving forward in that weld. And when your peak jumps back up, this is when you're melting metal and you're adding filler rod. And when it goes down to that background amperage, that's when you're moving forward a little bit, so on and so forth. Alright, and let's talk about the various types of electrodes. So I didn't talk about this a whole lot in class. I did mention it in the lecture videos. Just like with any other process, there are different types of electrodes, and they all do different things. They're all used for, different metals. Just to begin with, the classification. So as we can see here, designation, we have all of our ISO designations, which we aren't going to go into, and we have all of our American Welding Society designations. This is what we're paying attention to right here. So just like with all the other electrode classifications, this first letter, E, is letting us know that it's an electrode. Now the W I don't think I played this game with you guys this semester, but I always like to have a guessing game on what the letter W stands for in the classification for tungsten. So W is the chemical name, or it's the periodic name for tungsten, so wolfram. So if you look at a periodic table of elements, tungsten is it shows up as a W. Little fun fact for you. Now the next letter or next two letters, sometimes even, actually not three, just two. So the next letter or the next two letters are going to tell you what element has been added to the tungsten. So if we start with pure tungsten, meaning it's just pure tungsten, it's EWP, or electrode wolfram pure. And so this is identified by a dark green band. And let's start with this first one up here. So EWTH-2. So electrode wolfram, the TH stands for thoriated. And then the -2 is just the percentage of that alloying element that's been added to the tungsten. So 2% thorium, or approximately 2. It's like it's a percentage by volume. Now let's start with this third one, EWLA 1.5. So this is electrode wolfram lanthanum 1.5%. So over here you can see lanthanated 1.5%, and this is identified by a gold band, and so on and so forth. Serrated, gray band, 2% lanthanated, blue band, zirconiated, white band, so on and so forth. I will say that there are a few electrodes out there that are not pictured here, and I won't say they're specialty electrodes, but I don't want to give you too much to think about. We'll just keep it here on the basics. And then here's some more information about the various tungsten electrodes. If you want to, go ahead and pause here and you can go ahead and read through this. Otherwise, I'll just keep on going. So shielding gas. Shielding gas is going to be a really quick topic for us. There's not a whole lot to really say. There are really three. I won't even get into the third. I'll just keep it with these two, argon and hydrogen. So there are, helium. I should say helium. Hydrogen is also used, but that's specialty occasions. So sorry, we'll stick with these two, argon and helium. So 100% argon is the most commonly used shielding gas because it's inexpensive and it's not as difficult to get. So with helium, it's a little harder to get, it's a little harder to produce, and therefore that means it's more expensive. And it's going to be even more expensive because one thing about helium is it's lighter than air. That means you have to always have increased pressure for your gas in order to equate to proper shielding, to good shielding. So you're going to turn your pressure settings way up just to have enough helium come out and stick around the weld in order to protect it. Whereas argon is easier to produce, it's less expensive, and you don't need as much of it to protect the weld. So while helium does allow for a hotter arc, which gives us more penetration, argon actually helps to stabilize the arc and it helps to focus it a little bit better. And while that does lead to, I won't say less penetration, but just not as much penetration as with helium, because don't get me wrong, we still get great penetration with TIG, with argon. It's just our weld puddle is a lot more stable. Our arc is more stable as well. And like I was saying initially, there are cases where hydrogen is used in tiny amounts of other shielding gases. They're not as common. They're specialty occasions, so I won't really throw that at you just yet. But just know that these are out there. But for now, just know that helium and argon are the main two shielding gases with gas tungsten arc welding. Now there's another couple of things that the shielding gas does for us. So we know that shielding gas protects the weld, but it also helps in heat transfer. So argon, and this is where we start seeing the differences in penetration, is how the shielding gases can or don't get as ionized as the next. That's not to say that they chemically react, but just know that argon actually resists the heat of the arc a little bit better than helium, and this is why we get more of a focused stream arc. But also the shielding gas, before I get too far ahead, the shielding gas also helps to cool down the tungsten. So when you have a little bit of that post flow of shielding gas that's coming out, even though we've already kind of cut the arc out, that shielding gas helps to cool down the weld, but it also helps to cool down the tungsten. And so here's just a brief chart. Kind of talks about all the different metals right here. And if you're welding them with gas tungsten and arc welding, what types of shielding gases should you use? And then any additional notes about that shielding gas with that particular metal. It's a lot to go into. If you want to, you can go ahead and pause here, read over it. Otherwise, that's it, ladies and gentlemen. You made it through. I know this is a bit of a long video, but I hope it helped. If you have any other questions or concerns after watching this, I'm here for you. Please feel free to reach out. Otherwise, I'll see you in class. Thank you.